Good morning, dear students. I am Rizwana, working as an associate professor in the Department of Electronics and Communication Engineering, Government RIT Kottayam. We will be taking or handling the course Analog Integrated Circuits and Simulation Lab with the course code ECL331. A warm welcome to the class, my dear students, and please listen to this recorded lecture so that you will be able to do the TINA simulations software in a very simple manner. So please listen to this recorded lecture before you do the simulations that is actually coming in the curriculum of ECL331, which is Analog Integrated Circuits and Simulation Lab. So before starting to TINA is actually the abbreviation is Toolkit for Interactive Network Analysis. So before starting to the to our introduction or getting started with TINA, I would like to tell you about the assessment of this course that is given by KTU. So here you can see that the assessment that is this I have directly taken from the syllabus of KTU for the 2019 scheme, where you know that the marks distribution will carry an end semester examination and a continuous internal evaluation, and you also know that the external examiner will be coming for the lab external exam, that is lab university exam. So that carries this end semester examination marks with the external examiner 75 marks, that is 50% of the total marks. Total marks is 150. Out of that, the CIE, that is continuous internal evaluation pattern, is given here as attendance 15 marks, continuous assessment 30 marks, internal test 30 marks, that is usually conducted just before the second series. And coming to the end semester pattern also is given. End semester is nothing but the university examination for the lab, where an external examiner will be coming for, and you have to do for 3 hours lab individually. So you need to have a thorough knowledge in the analog and integrated circuits lab, even for you to do the mini project, etc. Usually the BTech students in electronics should aware of this software, and after that we will be doing the hardware in the lab after simulating it in TINA. So the experiments that is going to simulate, that is in the curriculum, it is saying the experiments to be done in a software. It can be either PSpice or TINA. So we will move to TINA, okay? And the simulation experiments are given like this. That is, the first experiment is difference amplifier and instrumentation amplifier. Second one is a stable and monostable multivibrator using op-amp. Third one is waveform generator using op-amps, triangular and sawtooth waveform generation. Wein bridge oscillator using op-amp with and without amplitude stabilization. Active second order filters, that is filter we are dividing it into active second order and first order. So second order we are doing it in it has a low pass filter and high pass filter, and the first order is band pass filter and band stop filter. All are using op-amps. And notch filter, we will also say it as the band stop filter to eliminate 50 Hz power line noise. This is coming too many applications while you are designing a project, because usually the 50 Hz power noise will distort the signals that you are getting. So it is very much useful for you to study the notch filter to eliminate 50 Hz power line noise. And also in that there is precision rectifiers using op-amps. And the seventh simulation experiment is a stable and monostable multivibrator using timer IC NE555. And the last simulation experiment is D2A converter using R2R ladder network and A to D converter, that is analog to digital converter using flash type. So to start with the TINA, why we are moving on to the TINA software? Maybe you might have heard of the PSpice or Spice also. But comparing with the Spice, okay, PSpice or Spice that you might have familiarized in your S3 or S4 labs, okay. So comparing with the Spice, okay, TINA is a powerful circuit design and simulation tool, and it is ideal for designing, testing, and troubleshooting a broad variety of basic and advanced circuits, which can include even architectures, even digital circuits, analog circuits, and even the peculiarity of TINA is without any node or number of device limitation. So in SPICE and all, we can see that there are some limitation for the device limitation, number of devices that can be used. That is not there in TINA. That is, you know that the TINA stands for Toolkit for Interactive Network Analysis. Whatever may be the complexity of the network, the TINA will do the simulation. And you can, TINA is actually introduced by, this TINA software is actually introduced by the Texas Instruments. TI, we will say the short form of Texas Instruments as TI. So here, what they are giving is, if you are already aware of SPICE-based simulation, then you can directly switch over to TINA. Okay, then adapting to TINA TI should be an easy and straightforward transition. And here you can see that the TINA is a powerful circuit simulation tool that is well suited for simulating the system or power supply as well as the analog circuits. And this tool is ideal for helping the designers and engineers to develop the test circuit ideas. So with this small introduction, I will start giving you like the getting started with TINA. So how can you start the TINA? So here you can see that initially, you know, any software that is to be installed in the system. So what are the requirements of installing TINA introduced by the Texas Instruments? The minimum hardware and software requirements for this TINA TI is IBM PC compatible computer running Microsoft Windows either 2000 or XP is enough. Then Pentium or equivalent processor and 64 MB of RAM, hard disk drive with at least 100 MB free space, and a mouse is enough. Of course, the PC will be having a monitor, or if you are having a laptop, is more than enough for you to do. For you, if there is no PC or no laptop also, don't worry about that. Our computer lab is having more than 30 systems, PCs, all installed with TINA. So when you come to the offline class, we will be doing the first week lab in the computer lab. Our Department of ECE computer lab, where we have already installed, okay, TINA software in all the systems. So you can directly go there, and if you are familiarized with this software, it will be fruitful for you to do the mini project that is coming in the 6th semester, and also the final year project, that is S7 and S8, for hardware troubleshooting. Okay, so please listen to this recorded lecture, so that it is giving a step-by-step procedure how to start for a student who is not aware or who did not do the analysis or the simulation in TINA. Okay, so we will start now. So the TINA initially after installing the TINA software in the system, it will be available here. You can see that the TINA, after installing, you will be getting a desktop shortcut. Okay, during installation it will be automatically, it will come in the desktop as a shortcut, and that shortcut, just double click on the shortcut, this schematic or this schematic editor will open for you. So this is usually it will come initially with a no name. After that, we can give file save as according to the name of the circuit. You can give, maybe if you are doing a Wien-Bridge oscillator, you can give Wien-Bridge, okay, or Wien-Bridge itself you have with the amplitude stabilization, please give it as Wien-Bridge with amplitude stabilization, and so on. So here, after you just click on the shortcut icon of TINA that is present in the desktop of your PC, the schematic editor, the TINA schematic editor will show, will be coming with the circuit space like this. So you can see that there are so many rows here. Okay, as usual a file will have the first row or the top row as the operations associated with the files, types of analysis, tests and measurement options, that is T&M, and so on. Okay, of course health will be a very important parameter in that. That is in the first row or the top row, you can say. And in the second row, again, what are things I told you, like if you want to open a TINA file or save it or do some wiring connection is here like this. So these are the file operations, text, hide, and wiring feature selection, etc. And the third and the fourth rows, here the third row buttons are the component type, and the fourth row tabs select the component group. So if I want to select a basic, so it is shown now with the basic. Basic means basic things, that is like ground, the power supply, DC or resistor, capacitor, inductor, the components, etc. will come in basic. If you click on switches, okay, so if you click on switches, what happens? I can show that here. If I click on this one, okay, you can see this is in the non-name schematic editor. I have just opened it, okay, with the shortcut icon. So here you can see that if I click basic, it will show, like now I have shown already in the PPT, also in the PDF also, these things all will come. And if we go and click on this will be transformer. This will show the name, that is non-linear, inductors, the capacitor, then potentiometer, resistor. These are all known to you, okay? And this is the voltage generator. This is the voltmeter. This is the ampere meter or ammeter, and this is the voltage source. And these are the basic parameters. That is, when you click on this fourth row, the tab as basic, that basic icon corresponds to all these things. If you click on switches, say for example, the third row has changed now, isn't it? This is the first row, I mean. This is second row, third row, and fourth row. So switches, if I click, okay, switches, then the switch, the symbol switch and alternate switch, the time control switch, and so on. And meters, the meters are very important, because meters are the things that will show the output. That is, we will say it as sink. If you have a source as generator, sink as the output. So meters, if you click, you will have a voltage pin where you need to take an output. This is always, you have to use this voltage pin whenever you are doing a circuit, because you need to see what is the output. Okay, maybe in some cases 1 or 2 outputs are required, so you need to click this twice, or you can have it as one click, then control C and control V, so copy paste. Or the second one, here you can see it is a voltmeter, it is an open circuit, this is ampere meter or ammeter, this is current arrow, the speakers, all the outputs, like we will say all the output points. Output points are selected whenever meters are clicked. And when sources are clicked, okay, whenever you are clicking sources, you know here, this is a voltage source, this is the battery is also a source, it is also coming, the battery is shown also in the basic icon also, and this is a current source, this is a voltage generator. And usually for you to have sine wave generation or square wave or anything, any input that you need to give, you have to give this one only, the voltage generator, okay. And there is a current generator also. So if you click on semiconductor, semiconductors, there you will get the op-amp. So that is the essence here. You have an ideal op-amp here and an operational op-amp. So operational op-amp you need to click always whenever you are doing this AAC lab simulation. Okay, whenever you need to have an op-amp, you need to click this operational amplifier. Okay, this is now I have already clicked. Okay, anyway, I will delete it. Okay, so click and if you click and drag and drop it here, it will be in the workspace or the circuit space. And the 555 timer, the diode, Okay, the Zener diode, the LEDs, the varicap diode, Schottky diode, the transistors, etc. are coming in semiconductors. And the last one, the SPICE macros. SPICE macros will give the special purpose ICs. Like you have an IC, if you click on this other components, any IC that you need other than this SMPS or ADC ICs, okay, you can have this from other ways. You here directly you have a instrumentation amplifier IC, okay, and a register voltage regulator IC, then current shunt monitor or the comparator IC directly. That is also available here. You can see operational amplifier also, it is there. Okay, so that is special purpose. Special purpose ICs or operational amplifier or ADCs are available in SPICE macros. So usually you are in for your lab for this time, for the time being, you will not be doing with the SPICE macros. And with the semiconductors is enough for you to do. Okay. So this is the basic thing for this slide. Okay, I hope you understood. Okay, so here this is the first, when you click on, it will come like this, and what all things are here I already explained. Okay, so then if you have to build a circuit, how will you build a circuit in the China, in China software? So the initial process is actually I will show it in the in the China itself. So if I am going to simulate a circuit like this circuit is an instrumentation. Sorry, this is an inverting amplifier. You can see that the positive terminal is grounded, so it is an inverting amplifier. It is a very simple circuit. Okay, for you as a beginner to understand, okay, I will just draw the circuit here, so that you will be getting how to wire it, or how to wire and arrange and wiring components, etc. All these things can be, instead of just like that saying this, I think you can you will get a more idea if I show how you can do this. So initially you need that circuit you have seen already. It is an inverting amplifier circuit. The same circuit I am going to obtain or wire it now, and we will do the analysis, or we will find the output. Okay, so here this is your op-amp, operational amplifier. So for you to get a more clear view, I am giving a view as a zoomed in view. Okay, zoomed in, so that you will have a bigger figure, so that in the recorded lecture also, if you are seeing it in mobile or something, you will be familiar to that. So first step is to click here and drag it and drop wherever you want in the circuit space. This is the circuit space, and initially you need an op-amp, because we are doing an inverting amplifier using op-amp. Okay, so the op-amp, which op-amp you have to select, that's the thing. So here in our lab, so simulation is done so that simulated output we have to verify in the lab with the hardware also. So in our lab, the MUA741C IC is available. So that is why just double click on this. Okay, I'm just closing it just to show. Go to this op-amp, OP1 asterisk, it is showing, exclamatory mark op-amp it is showing. Go to this op-amp, okay, click on that, then this window will open, okay, with the label OP1 parameters type. So in that type it is written as op-amp, and double click on that op-amp, you will have the catalog editor of the operational amplifier will show different op-amps. So in that standard, you can see all these op-amps. In that, you can see MUA741C is available. So click on that, select that. Okay. Then again, it will come back to the operational parameter OP1. Okay. So it will, that OP1, now it is, the name has changed to MUA741C, because we have selected that. Okay. Then for the MUA741C, we have to give a positive plus 15 volt and plus 15 volt in the 7th pin, and minus 15 volt in the 4th pin. Then only it will work. So for that, you need to have the battery in the sense the DC power supply. So for DC power, this is the battery, okay, DC power. So you click on and drag it to the 7th pin. Now you can see that this is actually 5 volt, but you need, this is by default in a battery is 5 volt. So you have to make it 15 volt, then only this op amp will work. So double click on this again, like the one I have done before. So the battery parameters, the voltage value, etc. will open. So you can see that it is 5. So please make it as 15. Okay. Then okay. Just nothing else is to be changed. Only the voltage we need to change from 5 to 15 that we have done. So that is like this. Then again, this one you can just do the control C, and I'm doing control V, so that because I told you, you need to have for the op amp MUA741C to operate, at the 4th pin you need to give a minus 15 volt, and in the 7th pin you have to give a plus 15 volt. So here from 7 you need to connect to this plus 15, and from 4 you need to connect to this minus 15. Okay, so and this positive should be grounded, and this also should be grounded. So what you can do is you can take a ground, that is from the basic, it is basic group icon, you will get a ground. This is ground. Okay, even when you click here it will show ground. Okay, so what I am going to do is I am connecting this point to ground, because the other point of the supply should be grounded, then only it will get the 7th pin will get as 15 volt. Okay, so this also should be grounded. That means here we are connecting it to like this, okay, to ground. So it will be connected to ground. That's it. Whenever a connection is done, it will show like this. Okay. So now the first step is over for the op amp IC MUA741C, because it will operate only if you give at the 7th pin of the IC plus 15 volt and DC, plus 15 DC volt. That is why we are using a battery. And the 4th pin you need to give a negative supply, that is minus 15 volt. Okay. So after that, according to the circuit diagram, I have already shown you the circuit diagram. So the circuit diagram, as I know the circuit diagram, I am just drawing it. So in that, what you have to do is you have to connect a resistors, that is inverting mode. Okay, as it is inverting mode, 3 can be grounded. So here you can have 3 to be grounded, and also an input is to be given. So for giving the input, you have to take the sources. In this source you have a voltage generator. I told you whenever you need to give a sine wave. So now we are going to give an input as a sine wave, and you need to check the output at the input point at 2 and the output point at 6. That is what we are doing. But the input is not directly given. You need to give it through the according to the inverting amplifier. It will give a gain of minus R2 by R1, where R2 will be the feedback resistor. All these things we'll be studying later in the theory class. And R1 is the input resistor. Okay, so for getting the resistors, again go back to the basic tab, then press resistor. Okay, just click on resistor and put it here. Okay, so again the same resistor, if you want you can control C and say control V. Okay, and that is going to be put here. But as you need a gain, at least I told you the value of the gain is determined for an inverting amplifier as minus R2 by R1. So R2 by R1 will give you the gain. If I need a gain of 10, what I will do is I will make this resistor value as, click on that, so the resistor label will open. Make it as 10K, so that I will get a gain of 10. So after that, actually I did not connect. So how will you connect it? You have to go and click on this cross mark. Okay, so cross mark, a ribbon like icon will open, so that it will be connected like this. Okay, again here, from here I need to connect to this voltage generator. This is connected, and the negative of the voltage generator, okay, should be connected to the ground. Otherwise, it will be floating. So now I think it has gone like this is okay, okay, like this. So here it is connected. Then what about 3? 3 for the inverting amplifier, 3 should be grounded. So it is like this, it is grounded. Okay. And this one, this is a feedback resistor. So the feedback resistor should be connected such that here you need to connect it like this. If you are getting like this, you can just delete that wiring. Just do it in a straight manner and like this. That's it. Okay. And here also, here this end should be connected to the output. Output is of the op-amp MUA741C is 6, so that is connected. And you need to check the input as well as output. For that, here you can see the meters. I told you the meters, a voltage pin can be clicked and dragged to this so that you will get the output from the 6. Okay. And if I want to check the input also, so click again the voltage pin. So if I need to rotate, like rotate in the sense this point should come here. Okay. So that is why what I am doing is just click on it. Okay. Like this, one hand icon will come. In that hand icon, okay, you can see that hand icon. In that hand icon, just right click. Okay. Rotate left, say for example. Again you just click on, then rotate left again so that it has become the position where we require. So now this is to be connected like this so that this VF2 is the voltage pin where the input will be shown and VF1 is the voltage pin where the output will be shown. So as an amplifier, you need to see the input as well as the output. And finally, the input is to be set. So here, by default, the TINA voltage generator will give you a unit step input. So that is what unit step. But unit step is not the input for an amplifier. So what you can do is you just double click on that so that the signal editor will open. In that, so many waveforms are there. You can see the pulse waveform, then the unit step waveform, the sine wave, the cosinusoidal cosine wave, okay, then the square wave, triangular wave, general waves, the random waves, all these things. Okay. So even the dot wave files, etc., all are available because TINA is giving so many applications. So the input can be anything. So here what you will do is you will just decrease the voltage because you are giving a gain of 10. The output should not be clipped. So here I am giving, say for example, a 0.5 volt, just reduced half of the default amplitude. And the frequency I am giving, say for example, 1 kilohertz. For example, you can give any frequency and check it. Accordingly, you have to set the output. That's it. Okay. So after that, now this VG1, that is the voltage generator, is fixed to a sine wave with an amplitude of 0.5 volt we have given. So that is also will be shown while you are doing it. Okay. So here, what I am going to do is now, initially, so here analysis, initially you can check that as it is an amplifier circuit. So if you want to, again, if you want to just mention the circuit name, say this is an inverting amplifier, so I can write, of course, inverting amplifier. Inverting amplifier, okay, maybe with a gain of, I have given a gain of 10 now, okay, inverting amplifier with gain 10, okay. So just click this one, okay, tick mark, and that will come here, okay, and you can drag wherever you need to have that heading. That is just clicking this T, okay, I have done it. So the inverting amplifier with a gain 10. And now we are just, if you want, you have to save because you need to submit these things after you do coming to the college and doing it in the computer lab. So go to file for saving, save as, okay, save as and I'm just going to the desktop now for the time being. Okay, and instead of no name, I am giving now the inverting amplifiers. A short form I am giving. You can give maybe full also, no problem. Inverting amplifier. Okay, so save. So it is now, it is saved in my desktop. And after that, what we have done is we have just drawn these things. Then you need to do the analysis. So if I am going to, if you want to find just the output, that is the input is given and the output you need to take for an amplifier, that means it is only the transient response. So go to analysis, like this analysis. Okay, in the analysis, just click on, when it has 1 kilohertz, okay, it should be in milliseconds, because 1 kilohertz frequency means it is divided by 1 millisecond. So 1 millisecond will be one cycle only. So if I give 10 millisecond, it will show for 10. Okay, so now you have got the output. This is the output. So here you can see this green color is the output, because it is the amplified output. You can see, of course, usually it will be, Tina will be giving like this. This is the input. Input is, we have given only 0.5 volt. 0.5 volt peak. That is, this peak is 0.5, because this is 2. 0.5, 1, 1.5, 2. And this one into 10 it is done. So here it is 5 volts. 0.5 into 10, 5 volts. If you increase this resistor value, this amplitude goes on increasing, that you can see. Okay, so this is the transient analysis. So this is already we have now done. Then also you can see other values, like if you go to analysis and if you give the DC analysis and calculate the nodal voltages. So for the DC, what are the voltages, or even you can give table of DC results. So if you just click table of DC results, what you can find is here. So just have a look on to the DC analysis. Okay, in DC, like I told you, in the analysis, okay, you have to click on, so that here you will get the voltages and the currents. Okay, just have a look on what are the currents and the voltages. So here you can see here actually 3. In 3, if you click, okay, it will show with the red line that VP3, this point, that is the voltage potential at the node 3, or node 3 is minus 15 volt. Here it is at 2. If I click, it will show as plus 15 volt, and so on. So this is what is the analysis, that is the voltage and the currents for the DC values. Similarly, you can find it for the AC values also. AC analysis. In the AC analysis, table of AC results. Table of AC results will show all the AC values here. Again, at the same nodes, what are the AC values? If we click on this 3, there will not be any AC value, because it is purely DC. So it will show it as 0 volt. And what is the VF1? That is the output. What is the voltage? What is the voltage coming? It is 5 volt, isn't it? Because 0.5 volt we have given here. You can see that this is 0.5 volt, 500 millivolt. That is amplified by 10, so that you are getting the 5 volt AC. It is AC, okay. And here, if you see, it will be AC will be 0, because here as if is only the DC is coming, so that will be 0, and so on. These things are clearly here, okay. And finally, what is the analysis that you can do for AC analysis? As it is an amplifier, you can get an AC, the analysis, click on analysis, then the AC analysis, then AC transfer characteristics. So AC transfer characteristics, if you click on, and if you just place 10 hertz to 1 megahertz, so that you can see that what is the frequency response of this amplifier. So if you press OK, it will come up with the Bode. It is actually the Bode stands for the frequency response, where you have a magnitude plot and a phase plot. So here you can see that from 10 hertz it is plotting till 1 megahertz, and of course at 100 up to 100K only. After 100K there is saturation. That is the normal range of this op-amp MUA741C. Before that it is all passing with a 20, this is 20 dB. This gain is 20 dB. Why? Because here you have in dB the gain. If you have the dB value, how will you get is 20 log to the base 10, log to the base 10 of the gain. The gain here is for this inverting amplifier with a gain of 10 we said already, okay. So that is 20 log to the base 10 of 10. Log 10 to the base 10, you know that is 1. So 20 into 1, 20 dB. That's why 20 dB it is starting, and it is until 100K it is almost 20 dB, and after that, because of the property of the MUA741C, it will attenuate. So these are the very simple example for doing, okay, and analyzing. So coming back to our PPT or the presentation, so I told you how to build, okay. So all these things now we have done already, but this is a recorded lecture. As you need whenever it is needed, you can go through that. Okay, then the analysis capabilities, I told you the DC analysis, how you can take. You have to go to the click on the analysis, then it will highlight and click on the DC analysis and calculate the nodal voltages. Okay, that is also here we have done the voltage, or and the mouse pointer becomes the probe used to probe the circuit nodes. That is, here you can see that in this already I told you how will you find the nodal voltages. I have told you the table of DC results before. In the same thing you can have the nodal voltages. That is, here in the analysis you go on to DC analysis, calculate the nodal voltages. Nodal voltages means it will come with what is the nodal voltage. That is, wherever you have given a voltage pin, there only the voltages will come. So this is DC voltage. So you know that here we have given pure AC, so that is 0 volt. But 22.6 milliwatt is there is a small shift coming in the output. And similarly, AC also you can do. That is analysis. Go to analysis, then the highlight on AC analysis, calculate the nodal voltages. That nodal voltages will be what? Will be the, yeah, that is only purely the RMS. Okay, that AC will give you the RMS value. That is, here you have given 0.5 volt peak, isn't it? 0.5 volt peak means it is actually VP by root 2. It will give you RMS that you have studied already. So the VP by root 2. So we can say it is 0.707 into VP. Into 0.5, that is this 353 millivolt or 0.353. It is RMS. And here also you know that it is your peak voltage is 5 volt that you have seen already, isn't it? So if you just cancel it and see the analysis and transient analysis, okay, you have got this, as I told you, the peak voltages. This one is 5. Even in this also you can just have the cursor. Okay, cursor can be put somewhere here, okay, and just it will show the values here. If you have, okay, if I am just varying the cursor, that values will be shown here. You see here, okay, here, and so on. Okay, if I am putting a cursor here, okay, for this analysis or for this input voltage, then I can put another cursor for the output voltage also. Then this is the for the output voltage. If I press it or click on here, it will show the output voltage. So here you can see that here it is showing 5.01 or it is 5. Okay, almost 4.99 or 5. So this is the 5 volt. This is peak VP, and here you can see that this VP with this, if you click on the analysis, okay, and if you click on this nodal voltages, okay, so it is showing, you can see that, okay, this is here it is VP is 5 volt, so 5 by root 2. 1.414 will give you this 3.54 as RMS. Okay. So this is a very simple analysis of a simple circuit that is inverting amplifier with a gain 10. So I hope you understood all these things. So then we will just move on, cancel this for this, and here just take the continue with the presentation. So this we have already, I told you how can you do that, this one, these things, DC analysis as well as AC analysis. Okay, and the analysis of transient, that is coming under the AC analysis, the transient after the AC analysis, after the drop down menu, after AC analysis comes the transient analysis. Here you can see transient, and for getting this is the same thing that I have shown in that. So from that only I have just taken the snapshot. So click on analysis, this one analysis, then highlight and click on the transient. Okay, then set the start and end times, etc., and click OK. Then you will come with the transient analysis from the simulation of this. So again, here you can see that these waveforms, by seeing the waveforms, you can see that this is an inverting amplifier because you see the phase shift. So for the positive cycle, the amplified waveform is a negative cycle, negative peak, and for the negative peak, you are getting a amplified output as a positive peak, and so on. So I think you have understood this transient analysis, and also finally you have the AC transfer characteristics. That's what I have shown again in that inverting amplifier with the gain 10. So here that is the Bode plot with the 20 dB gain. For that you are again doing the schematic editor analysis, AC analysis, and AC transfer characteristics. In that you can set the start and stop frequency. Accordingly, this frequency start here, as I have set the start frequency as 10. Okay, it is starting at 10, and I have set the stop frequency as 1 meg. That is why like this. If I need to give another start frequency and stop frequency, this will come whenever you are doing the filters. That is, I told you, the low pass filter, high pass filter, etc. You need to do the filters with the AC transfer characteristics. So in that, if I want to say in this you can see that for the AC Bode, here already we have placed AC Bode. You can see this one is from 10 to 1 meg. That is why, because I have selected like that. If I am putting again another the AC analysis and AC transfer characteristics, and if I am putting say 1 kilohertz from 1K. 1 kilohertz means it is 1000 hertz. Either you can put 1000 or you can put 1K. 1K means 1 kilohertz means it is 1000 hertz. Okay, and 1 megahertz. So this is capital M stands for mega and small m stands for milli. So here, if I put instead of like 1000, if I put 1K to 1 meg, then what is the difference you can see? Okay. So I say it is starting at 1K, 1 kilohertz, then 10K, 100K. It is multiples of 10. Of course, the Bode or the frequency response analysis, usually it will be multiples of 1 decade. 1 decade means 10. So 10, 100, 1 meg, and so on. Okay. So it is, you can see that according to your wish, you can do different waveforms. Okay, you can different waveforms in the sense different analysis. The same analysis, different parameters. That by just varying the parameters, you will be able to get the according to the design, you will get the output. So this is the same thing that we have already done. Click on analysis, set frequency range, and you will get the AC transfer. Lecture itself, so that it will be clear to you. So if I have like this, I may just, if you want to do one more circuit or another example, you can go to this file, then new, just click on new. So a new workspace or new circuit space will open. So in that, as I told you, I am going to do with a triple file, that is a stable multi-vibrator using triple file. So this triple 5 IC I have dragged and put it CA555. Already it is 555, so there is no need for going back to again double clicking on it and changing. That is not needed now. Okay, so here the 555 IC, maybe you might have studied or not, I do not know. It is having only 8 pins. That is the four pins here, 2 pins here and 2 pins. It is drawn like this, but the IC chip will be having all the 4 here and 4 here. So in this, there is a VCC. Okay, of course you need to give a VCC from the basic that we have done before also. Click on this battery, then drag and drop it here. So here, this is a, say for example, it is a 5 volt. For 555, it is 5 volt is enough. Maybe you can put 6 or 9 also, no problem. But don't put 15 volts. Even with 5 volt, the 555 IC will work very good. Okay, so I'm not changing that. It is V1, it is 5 volt itself. So that is to be connected in between the VCC point and the ground point. That is the initial thing. And the ground you have to, again I told you, the ground you have to take it from here, drag and drop here. Okay, just for you to understand. Okay, because I have done for ECL331 IC only. So as you need to do, this is the ground connection, and here this one should be grounded. Okay, this is grounded now, and the plus positive point of that 5 volt should be connected to this. Sorry, here positive point is to be connected to VCC. Okay, this is connected to VCC. So that is over. Initially, whenever you are dragging and dropping an IC, first step is to give that IC the supply. Otherwise, you may forget, then the IC will not work. So for this IC plus 5 volt, we have given. So that is the first step. And after that, the 555 to function as a monostable, what you have to do is you have to just connect the trigger and the threshold together. So this is the threshold pin and this is the trigger pin, and that trigger pin will be connected to our capacitor which is coming in the design. So this point, again you can take a capacitor from here. So if you can put it here somewhere. Okay, so that capacitor, okay, the capacitor value and all you can change. Maybe the capacitor value for this design, I am using only a 0.1 micro, so I can put a 0.1 micro here. So that will be produced as 100 nano. And here what you can do is here from this threshold and the trigger, the threshold and the trigger is to be connected. So now I am just connecting this to the capacitor, and the trigger point selected and connected, so that this threshold and trigger is now connected, and that is connected to the capacitor one end, and the other end of the capacitor is to be grounded. So the other end of the capacitor here, okay, this is your ground point. So now it is grounded. Okay, that is the second step in 555. And also from the here you have a CONT, that from that you need to have a capacitor of 0.01 microfarad, that we will say it as a parasitic capacitor. That is the capacitor to avoid the noise. So and one more capacitor you can put from here. Okay, and that capacitor is, maybe you can put here itself, no problem, because the other end of the capacitor will be ground. Okay, so here this capacitor is not 100 nano, it should be 0.01. Okay, this is selected as 555 now. So here this capacitor, so this capacitor, okay, what we will do is just to change the capacitor. You can select the capacitor, move on to the outside, then select here, then make it as 10 nano. 10 nano is more than enough, even 1 nano is okay. So then just click on, then move it, so that it is already done. Even you can place it here to reduce the size. I have put it here. So here what you have to do is, here you can take it and connect it like this. Okay, and this one is again connected to the ground. So that is the third step that we have to do. And here in 555, the reset and the power supply pin, that is the VCC pin, is to be connected for the 555 to function as a monostable. So that is connected. And what happens to this discharge? This is the discharge point of discharge pin of the 555. In that, you need to connect the resistors. That is, one will be to the capacitor and the other one will be to the supply. So take resistors, okay, here. So as I am connecting in the rotation fashion, that is, I need to have the resistor in the top down fashion. Just to do that, rotate it left, okay. Then again you can do one more, and again rotate it left, so that it is both of them, okay. And the capacitor values and all you can design accordingly, according to the what is the time period that you need, okay. So accordingly you can select, okay. So here I am clicking here because this is to be connected like this, not to the output, but these 2 points that is to be connected here, okay, that is connected to the discharge pin like this, okay. And the other end, okay, this should be connected to the positive supply plus 5 volt, and this should be connected to this capacitor, that is this will form the RC time constant of the monostable. So here you can have it, okay, like this, and connect it to this capacitor, okay. And here the out you need to have, and it is not 1K, we can give a value around 10K, okay. So that is the designed resistor value number. So if you change accordingly, that a stable multi-vibrator the output will change. So here, and finally you need to check the output. For that output, I told you, from the meters you need to have a voltage pin. So this voltage pin is connected here, okay, and I'm connecting that to the out pin here, this to the output. And if I need to check again the capacitor voltage, the capacitor voltage will have a very much influence for the stable multi-vibrator. So the capacitor voltage you can find, this capacitor voltage, that is not this capacitor, not the capacitor, this capacitor, that is the capacitor voltage, we will say VC, okay. So the capacitor voltage we need to find means we can connect it to either to the trigger point or to the threshold, both are connected to the capacitor, and also this resistor also the same point, okay. So here if I am again taking as the same way in the inverting amplifier that I have done, just rotate it 2 times, so that I will get a so here in the there will be a hand icon coming, okay, and at that time only you need to click on, so that it will rotate, okay. And here what you have to do is you just give it to the trigger pin or threshold pin, both are shorted, or this capacitor point or this resistor point, all are the same points, okay. Any of the point you can give, so that will be the capacitor voltage, okay. So I think this circuit drawing is over now. Now you can just find the output. So here you can maybe you can recheck also whether the VCC is connected to plus 5 volt, and also this reset is connected to VCC, and the ground points are all connected, okay. So this is the capacitor, this other end is grounded, and this resistor point is connected to the capacitor, and this is to the plus 5 volt, and so on. So here if you want, you can just check the DC analysis, otherwise just go and simulate. Now even if you want, you have to save it, so you can give it as save as a stable multi. In desktop itself I am giving as a stable, it is actually using 555, okay. Before because you are using a stable using op-amp also, you are doing, that's why just to differentiate between the 2 names, it is better to give a stable using 555. And you just go to the analysis, and just go to the steady state solver and give this 10 millisecond. I have given 10 millisecond, and this 100, it should be 100. By default it will show milli, but it should be 100%. Okay, so maximum searching time is 10 millisecond, and this is one final, first final checking time is 1 millisecond. You can just try it, what is coming. Okay, what is the output showing. Okay, so it is just this is the output for the stable. You can see that here the stable amplitude, and here again if you want you can just go and because starting there will be a delay, so that delay is coming here, so that is why even you can just start at 1 milli also. 1 milli, 1 m. Okay, then it will show from the 1 millisecond only. So 1 millisecond, you can see here from the 1 millisecond here it is, this is the on time for the stable will be actually 0.693 into R1 plus R2 into C. So that is why it is having twice the time period that of the off time. Off time is only R2C. 0.693 R2C. So that is why this one is to make it symmetrical. Only thing is you can just give a diode, okay, in bit just to make the symmetrical waveform. If you want a symmetrical waveform, just you can give a diode in between. So that is diode in between, in the sense in between this discharge point and that is across this R1. Across this R1, if you put a diode, this can be made, that you can see, you can do, because I have asked you to do the asymmetrical and symmetrical. So this one it is with the duty cycle not equal to 50%. So here go to the text and you can put the name. This is actually asymmetrical stable multi. Asymmetrical. So asymmetrical stable multi using 555, that you can see from the circuit diagram. It is 555. So if you why it is said as asymmetrical, because this on time is not equal to off time. This on time is double that of the off time. To make it symmetrical, what you can do, like I told you, maybe I can just show that, like go to the semiconductors and take a diode, okay, and diode, it should be in this manner, that is upside down. Just rotate right, so that it will come down, and this one here just to put it in between. So in between this, okay, these 2 points. So here if you put a diode in between, okay, that is, it is actually across the resistor. So here the diode, this point should be connected to this resistor, that is discharge point only, and the other point would be connected to this point, that is, this is the resistor point. But just to avoid, or just to have the symmetrical stable multi, if you have like this, and you can have the analysis, and again with the same steady state solver, okay, you will get the same thing with the on time equal to off time. Now you see, just to connect this, it will be then now positive half, the on time means this positive half. Positive will be equal to the negative. And this capacitor waveform from will switch from 1/3 VCC to 2/3 VCC. So that you can see from here, this is 1/3 VCC, because 5 volt is the VCC. 5/3, of course it will be 1.67, something like that. So, and 2/3 VCC, 2/3 of this one will be almost 3.6 or 3.5, like that. Okay, so this is this red color is showing the capacitor waveform, that is VF2, and the VF1, the output is the green. So this is the just the monostable, just to show the symmetrical, as well as the other one, the asymmetrical, isn't it? This one without this diode. This is with this diode. Okay, so you can just do trial other things just like that. The other softwares will do. You can do it. Okay, very big thanks. Okay, please listen to this recorded lecture so that it will be useful to you. I hope you have understood something. So please feel free to ask any doubt. Okay. Okay, thank you.